All right, the goal of this video is to talk about problem 36.5 on page 49. We're just going to make some of these plots. You'll see them all the time in books, and I wanted you to know how to make them. It's good practice to know how to plot stuff, and the faster you are at making high quality plots, the more employable you'll be. And I do think every once in a while there's some weird little issues that show up in plots. The more plots you make, the more of these weird little issues you see, the less you get hung up, the better you look at work in your future career. So let's start with a screen share. And here's the equation that we want to use. It's pi a over lambda times sine theta equals beta. So I've color coded that one column here. And this is the intensity function that we're trying to model right here. For reference here, there's a slit right here, let's say, and then there's some angles from the midline. So this would be theta. And here I'm going to say theta above the midline is positive and below the midline is negative. Right? So the midline corresponds to theta equals 0. All right, and notice here you can have angles all the way down to, say, negative 90 degrees, and you could go all the way up to positive 90 degrees. Now, if you want to see how that relates to the position y, we can discuss that after we get the angular plot made. So let's first focus on making the angular plot. All right, annotations, let's get rid of those. All right, and what I've done here is I've actually named some of these constants up here in the name box. So, right, like let's say I wanted to name this taco. I could name it taco. So I just type in the name, hit enter, and so that's how you name it. But so these are the ones that I want to use, Imax, lambda, and A. You'll notice that instead of using the one that's in units of nanometers, I'm using the one that's in units of meters. So I basically converted everything so that I won't have any unit issues. I'm trying to use all those highlighted cells here. Let's maybe put some borders on there so it's easier to see. All right, I'm using these numbers that are in meters. If you're curious what to do to get from nanometers to meters, you could just say this is equal to that thing. Wow, now it's got that name on it. That's funny. Times 1e negative 9. And then again, notice I've called this one lambda, this one I've called just A, and this one I've called just L. Now, I recommended in this problem going from, say, negative 90 to positive 90 in increments of 1/10 of a degree. The reason is this plot curves wildly and rapidly. I can even show you what the plot ends up looking like. It ends up looking like, versus degrees, this one. And if we zoom in a bit and look down here, this is what we're trying to make. You'll notice that it's changing quite rapidly. So we're going to need multiple points per 1 degree to get these peaks to show up right. So what I'm saying here is that's why I'm choosing to go by such a small increment size. So now I'm going to highlight the first two numbers, grab the bottom right corner, and go till I hit positive 90. Almost there. All right, and now a trick that I like to do is I'm going to go back and highlight a bunch of this stuff. I don't like scrolling down that far every time. I know that there's going to be some issues at 0. So maybe I should highlight, well, we'll come back and get the 0 point. You'll see what I mean. So I'm just going to shrink these down to 1 pixel. If I hide them entirely, that can be kind of nice. If you hide them entirely, the plot won't look right away. So now there's this huge gray field from all just the borders, but just showing you. It does go all the way down to 90, all right? It just means less scrolling for me while I'm doing my scratch work. If you're curious how I got the Greek letters, you can change it to the symbol font, SYM, hit enter. That's how I got the Greek letters. This one, I just did a screenshot off Microsoft Word. All right, there's another Greek letter. Okay, cool. I guess I should, oh, sorry. If you don't know how to do subscripts and superscripts, you highlight there, format cells, and you can either subscript or superscript. Okay, there we go. All right, so now I'm going to use the radians command to convert this. I don't have to fill down now. I could fill down now. Obviously, if you double click the bottom right corner, that's a fill down. If you drag it down, you could do that. But what you don't want to do is use this cursor. Notice it's a small black cursor with arrows. That moves things around. That's not what I want. So you got to mouse over the bottom right corner. Notice there's no arrowheads. And you can either fill down like this manually or double click down. All right, this one, that's just sine of the angle. You got to use radians for Excel. All right, and then beta, this is equal to, let's see, pi, which is a function, so you got to remember those parentheses there, pi times a over lambda, whoops, there it is. All right, and so that gives me beta, and then this term is equal to I max times, let's see, sine beta. Oh, do I have that yet? No. I'm going to do this. I'm going to not screw up my parentheses. Whoops. Screwed up. Equals whoops, come on now. I'm having trouble typing. I max times something in parentheses squared. Then I'll go back in here and we'll type it in. It should be sine of beta, which is what, D5? Yes, divided by D5, enter. And now I can crank this, I could change the number of sig figs, crank this down, and now I'm gonna make a plot. So it's easier for human beings to understand in degrees, so let's make the plot in degrees. Highlight the first column. Now, my hands are off the keyboard. Now I'm going to press and hold Control and highlight this one on the way back up. I need to move something up here from my Zoom. Whoops, I lost. Okay, there we go. I'm going to hit Insert. And then, oh, let's see what we got here. 100E4. All right, and so there's something clearly going wrong here with this plot. What did I do this time? Oh, I forgot to fill down the sine function. Do you see that? Forgot to fill that down. All right, hopefully this plot will auto-update. If not, let's just do it again. Sorry about that. All right, that didn't fix it. Let's go. What's going on here? 99. Okay, we see the sine functions changing. We see the angles changing. Why are we getting 100? Am I going to have to re-record this video again? Let me make sure. Let's check one last time. What did I forget? Oh, I forgot to multiply by sine theta there. Do you see it? Okay, so let's fix this up. So beta needs to be times sine theta. Whoops, times C5. Sorry about that. That's going to change things a little bit. There we go. And now we see the interference pattern showing up. All right, sorry about that. Took me a minute there. Now, an interesting thing here, if we look carefully here, you're not going to see much. Let's make this look like a number here. Oops. Let's go from 0 to 100, and let's change this number to just a normal looking number. All right, and then the angular axis probably makes sense to go from -90 to 90 by 10s. We could have this be by 5s. And then just so I can see things a little better, let's cut the decimal numbers. All right, and so we can see this a little bit better now, but in order to notice one interesting fact here, this peak is at 100, and this peak right here, if you remember, I think was at 4.5. If we did the previous problem, we found that the ratio of this brightness, of the first bright, to the central max was 0.04503 or something like that. So we expect that this number should be about 4.5. So one thing we could do is, we know the central max is crazy bright and all the rest of the interesting stuff is down here. One thing we could do is to, whoops, and let me get this. I'm going to just scale this. Let's go to this axis. Oops, let's get on the axis and let's go to just 5. And now you can see all kinds of crazy stuff. And if we wanted to, maybe, we know this pattern is symmetric. Maybe another thing we could do is we could look from just say 0 to 90. And so now you could start to see the pattern a little bit better here. Here, I guess I better include a decimal place on that. Otherwise that looks kind of funky. All right, and so you can see, you can mess around with this a little bit, but hopefully you can see this interesting pattern here. Finally, one last thing. How do we get the position involved? Well, if you wanted to do this again in terms of position, what you could do is you could change this, and you could make this y, and then you could figure out sine theta using this equation. Remember, when we have this single slit interference pattern, here's the slit, here's the midline. The vertical distance is y, the angle is theta, and this length is L. So from the Pythagorean theorem, this side is L squared plus y squared. And so you could use this formula and get another pattern. And I actually have that somewhere. Where is that one? Whoops. I don't know. I think I may have closed it out already, but that's okay. That gives you an idea. And so hopefully you can make this plot now. In the next video, we'll talk about how the single slit can be overlaid on top